We are going to talk about theory of quantum channels for photonic quantum networks. My co-instructor is Brady, who is also at USC. All right, let's go ahead and then go into the contents. Anthony, can you go to the next slide?
Yeah, sure.
Okay, next slide. Yeah, today we're going to begin with the introduction. So we're in the era of quantum engineering, and as you guys know, the CQN has a lot of efforts in quantum networking, which is part of the quantum communication, where there are lots of applications, including teleportation, key distribution, entangled state communication. But moreover, the role of quantum network will be able to actually enable non-classical resource to be shared at distance. These are very powerful resources for both sensing and computing. You can do distributed quantum computing. You can also enable entanglement between sensors far away from each other to actually do better than just individual sensors. So the other two applications are quantum sensing and quantum computing. And these numbers are not a state of art, I believe. These slides are, it's hard to keep to the most updated versions, but probably I think IBM has 128 or if not more right now, a number of qubits. And in the NISQ domain, people are talking about is there some valuable computation that can be completed by these near-term devices? And in sensing, people are now trying to bring quantum sensing to real applications and see how it will enhance biological or chemical or other sensing problems. All right, next slide. So in terms of quantum networking, as I mentioned, it's closely connects everything together, connects sensors. So these sensors have many applications. For example, even for fundamental physics study like dark matter search, people have now realized that using quantum sensors to actually measure things more precisely. And because dark matter and things related to fundamental physics like gravitational wave are so weak, so you would really need to have quantum sensors enhanced by squeezing or entanglement to actually gain advantages and speed up the searches for fundamental physics. Can also connect classical transceivers to these quantum networks. And in this case, you would be able to do quantum key distribution and do quantum secure communication and many other more classical oriented applications. And of course, just quantum computers, as I emphasized, the fault-tolerant version has the hope of solving hard problems with advantages. And also, it's important to connect a bunch of them so that we can enjoy both the scale of larger system. This is not only just kilometers apart, even within the same computation center, you might want to have a quantum network to actually connect smaller computers together to complete larger tasks. All right, let's go to the next slide.
Someone asked, should we be seeing a cursor? You're not using the cursor, are you?
I'm not using the cursor. Are you? I think you are using the cursor, right?
Oh yeah, that's right. That's
Yeah.
right. Okay.
So you probably can put the cursor somewhere, and then if needed, I will actually mark up and yeah. So markup would be coming from me.
Right.
Right. Yeah. So and many different physical platforms and systems are involved in these applications. So those quantum computers, the big companies are investing in mostly in microwave superconducting cavities, or these based transmon qubits. But there are other systems like trapped ions also are very promising. And those are for computing, and the NV centers, readable icons are also very promising for quantum simulation. But there are many different physical systems. So it's very important to actually know how to describe each system. But to start with, we need to actually learn the basics of how to describe quantum information. These tools we're going to talk about today actually allow you to describe a lot of these systems, even though they are very different in the physical realizations. All right, let's continue. So here, for example, there's the quantum optical information processing example. where secure quantum communication network is being demonstrated. And these are examples of how powerful photonics can be. And in figure B, this is an example of quantum repeaters demonstrated that enhances quantum communication. And this just happened very recently. So really, we are in the regime where quantum networking is becoming more and more realistic. And at least for small scales, we can already implement them in labs and in real applications. Let's continue.
Great. So first poll question, just there's a few of these throughout, I think about 5. Just to keep you guys a bit awake. And here's a 0th order one, just to start things off. So where is the poll? There we go. Polls. Okay. Poll 0 launch. Okay, great. So I open the polls. Yeah, so simple question. What are photons good for? Okay. So Quntao talked about many platforms, many different applications, and these are 3 primary ones. So what are photons good for? Okay, great. Can you see the screen? The poll?
Yeah, I can see the screen. I don't know if other people can see it. Probably yes, I think so.
I'll stop sharing anyways because I think it's on the next. Yeah, I mean, photons are quite versatile, right? So several quantum computing architectures, at least in principle, exist based on linear optics. So you have optical photons or microwave cavity modes. And so there's some ideas in bosonic quantum information processing with microwave photons. Also, many quantum sensing platforms. You use squeeze light, for example, that's being used at LIGO currently. And finally, yeah, I mean, it's for quantum communication, basically all of that will be done, or most of that will be done by optical photons, at least over very large distances. So, yeah.
Yeah, it's important to note that although traditionally we say photons, we mean optical photons, but microwave is also photons. So the theory we're going to learn today, quantum channels and also those bosonic channels, they actually apply to both optical frequency, microwave frequency, and different frequencies. And it's also understandable people might choose communication. In the previous slide, I see 12%, because indeed in the state-of-art systems, I mean, the best computers, quantum computers right now is not optical. Although optical is of course important part of the controls. A lot of these, for example, ion traps, you use optical to control, etc. Right? So that is true. And in sensing, though, photons are always important, LiDAR, radar, etc. All right, so let's begin the quantum channels general description part. Next slide. Right, so today we're going to use a bunch of symbols. So we use calligraphic H for Hilbert space, phi. These are direct cat notations, direct notations we're going to use. And sometimes we will not use hat all the time. Sometimes we might miss it, but density matrices, we usually use rho. Additive operators, the unitaries we use, try to keep hat there to know that this is an operator and different. And the quantum channels will use this cal n, cal l, for example. These are just, traditionally people use it. L might be standing for loss in some cases. And A and A dagger are creation operation, annihilation operators, and Q and P are momentum operators, and they're related to each other in this case. For example, Q would be the real part, which is A plus A dagger, and P would be the imaginary part, which is A minus A dagger, up to some scaling factors. And H, Hamiltonian, vacuum, and 0 and 1, we try to denote it differently so that it's not confusing. All right, let's go to the next slide. So let's begin with fundamental understanding of what's the word like. So one sort of understanding around quantum physics is that if you take everything together, usually we have a system on the study, and then there's a reservoir we know that it interacts with. But even beyond the reservoir, there were everything else that is the environment. And if you include everything together, the hypothesis of quantum physics is that this should be described by a pure state, and it goes to unitary dynamics. So this is a fundamental assumption. So this means that if you learn unitary dynamics, learn things about pure state, and also know how to do, partial trace or look at subsystems, then you should be able to describe everything, including those quantum channels happening, right? So there is a unitary description when you include everything. And whenever you see a mixed state, it means that some information leaked somewhere that you haven't included. So in principle, if you include more, you can describe things still from a pure state and the unitary perspective. Okay, next slide. So there comes the mixed state. That's because if you actually don't have the full access to the whole system, then if you have partial access to the system, instead of a pure state of the whole system, it becomes a mixed state. And mathematically, this is something called partial trace. So let's say you have a joint state of the system and the environment in a pure state, SE, in a pure state phi. And you can always write this state in some computation basis. In this case, it's convenient to choose the basis such there's a Schmidt decomposition. So meaning that the wave function of SE can be written as a superposition of same index I on S and E, with lambdas are the common eigenvalues. And this is always possible, promised by some mathematical theorem, but in the quantum physics level, it means that we can always do this trace easily. If you get rid of the environment and focus on the system side, then this is called something called trace. In this particular case, it's okay. We didn't write the whole thing out here. This is writing part of it. So in principle, you would write down phi SE, that will be the whole density operator. And then let's say this is the rho SE.
Yeah, that's right.
And then rho S would be trace of E, rho SE. And when we say trace, you can understand it different ways. One way to understand is maybe, okay, we want to maybe measure the system E and sum of all the possible measurement outcomes so that we are not post-selecting anything. That means we are discarding it. It's equivalent to measure and then throw away the results. And this would be a partial trace. This is so-called partial trace. And you can calculate this explicitly, input the Schmidt decomposition. Let me
Yeah, sorry about that. I butchered this equation. I think the rest of them in the slides are fine. Butchered this one.
Yeah. So, okay. Let me see how to, so there's a window where, okay, I minimized the window where, yeah, okay, good. Now I can write here. There was a zoom window appearing there. So now you need to be careful with the summation index because I is the summation index I'm using for tracing out. So you need to use dummy index J for the first summation. This is Bragg part, and then there's a cat part, which is the dummy index for the K. And this is SE, and then I is on E. So this would be the whole complete formula. And you will notice that I get an inner product with J, so then you get a delta Ij. And K get a delta inner product with I, so there's a delta Ki. So eventually, all these delta, direct deltas connect, and then you're left over with this final result with the system. And the lambdas becomes the eigenvalues of the system, which is indeed the case, should be the case, because there's a Schmidt decomposition. And also, you can interpret these lambdas as the probability of outcome J if you were to do any measurements. All right, let's go to the next slide.
Okay.
Let me clear the, yes. Okay. And so this is the forward process where we, start from the pure system, and we say we focus on a subsystem. So we have a SE, whole system pure, and then you focus on S. That's the forward where you come from a pure state and then do trace, you get a rho S. And then the reverse question can be asked, if you are given a system in a state rho S, can you construct the whole system S and E such that the whole system becomes a pure while the small system S is indeed in the state rho S? So that's the reverse question. And indeed, there's a process just to reverse everything we've done. So if you are given a state rho S, the canonical way of writing out a purification would be to first diagonalize it. So rho S is in its eigens values decomposition. And then you just make use of the fact that you can have Schmidt decomposition, and then you construct the essentially append environment digit here with the same index J, and then you can have the SE pure state. So sometimes you might need to bring in not just a single subsystem. So if you bring in some subsystem E1 that is not large enough, and you find that SE1 is not pure, then you can extend the environment at E2, etc., and then to make sure that everything is pure. And from the fact that you can do Schmidt decomposition, it means that to purify a D-dimensional system, you just need a D-dimensional ancilla at the most. So this is the true. This is the case. Of course, you can find even a larger one. You can still purify it. But sometimes if you have a smaller ancilla, you might not be able to purify it because you are not be able to describe the correlations between S and E if E is too small. All right, let's continue. And here comes the dynamics. So now that we say you can have a universe, and then we look at a part of the universe, which is system S. So what's going on with the dynamics? Well, the hypothesis of quantum physics is that all dynamics are unitary eventually. So in this case, if you include the environment, if you include a large enough environment, you should be able to write down any process happening on the system by a unitary USE. And after the interaction, assuming that you already have some basic knowledge of quantum mechanics, you know that pure state is unitaries involve, on any quantum density operator rho. In this particular case, it's a product state. On this rho, SE, you would evolve as a U and the U dagger acting on the left and the right. This comes from if you have a pure state SE, which might not be always the case, then you will evolve under a unitary by SE in this form. If you are not very comfortable with direct notation, then you can think about this phi as a vector, and the U here would be a matrix acting, multiplying this vector. So this is the way you write down the vector transform. But the full description of state, we use density operator. It's itself a matrix, but it's depending on the whether it's pure, the rank could be 1. So in this case, we can write down, if it's a pure state, we can write down SE like that. And because state, if you want to do the conjugation, you obtain SE, USE dagger. So therefore, when these density operators go through unitary dynamics, we have USE, rho SE, USE dagger. And this applies for not just pure state, this applies for mixed state. And in fact, when we describe interactions, general interactions, in this case, the S system and the E system, they are initially not correlated. So they are in general, in this case, in product state. This makes sense. For example, when you send photons through fiber, the photons you prepare shouldn't be correlated with these noise photons in the environment. If you have a good lab and you filtered and shut down those unwanted couplings. There were cases where S and E, they could be correlated. And in those cases, then you would actually need more than a quantum channel to describe it. You might need sometimes a quantum channel with memory effect, or maybe you just describe it by general unitary dynamics, and then the quantum channel picture would not work in those cases. Okay, back to this picture. So now we have an environment and a system. They are not correlated initially. So after this unitary interaction, they are probably correlated in this case. And of course, then the question is, we previously said that, okay, if you include everything, it should be a pure state. So now why we have a system, environment, and we still write a mixed state density operator? It could be mixed states. Well, here we are thinking about the minimal description of this unitary dynamics. So if you really want a pure state, you can always add another system. Let's say another system, let's call it B, for example, that purifies S and E, and that system remain unchanged through this unitary dynamics. So there's identity. So in that case, you can extend the picture to pure state, evolve under unitary, but a lot of time those B are not necessary because it's never going to appear in any of these analyses. So we sometimes just left out B just to keep S and E in this case. All right, let's continue. So once you understand that there's a unitary dynamics on the system environment, then to get the output state, which most of cases we just care about the S prime, or in some cases we only have access to S prime and we don't have access to the environment. The environment could be these photons lost to the outside of the fibers, and therefore you have no access in getting them back. So either by choice or just out of no control over the environment, you only focus on the output system rho S, and this is the way you obtain a general input state rho S and to the general output state rho S prime. And this is what we call as a quantum channel. It's a map between the input state to the output state, and we often write as a calibrate N, or sometimes calibrate, sometimes using phi, or these are often popular notations used for denoting channels, sometimes L standing for loss, many other possible choices. And this is a linear operation, linear in the sense that it's a base superposition. So linear, the word linear has a lot of meanings. In quantum optics, it means something different than what we mean here is the linearity for quantum physics. So if you have states, probably mixture of states or superposition of states, then the output is also the property mixture of these particular rho S and the tau S states. This language of describing a quantum channel in mathematics is called a so-called CPTP map. It's completely positive because it maps quantum states and two quantum states, and quantum states are so-called completely positive because if you measure it, these probabilities are positive. And trace preserving means that the probability is conserved to 1, it's normalized to 1. We are not doing conditional operations. Here it's a quantum channel. And there's a separate description of conditional maps. If it's not trace preserving, then you can say condition on some result, the state is mapped to some other state. There's also mathematics to describe that, that's conditional maps. But here we focus on those trace preserving ones to include all the cases. So it's called the quantum channels. An example I was using already is that output state of a photon after transversing a single mode fiber. You can think about it as a quantum channel, and many other things are quantum channels. For example, all the noise models in quantum computers can be modeled as some noise channels. If it's memoryless, meaning the environment is random enough. Sometimes could be correlated quantum channels between multiple qubits or multiple photons, but that's still a quantum channel as a with a larger input systems. Right, next slide. So we can define quantum channel from the unitary evolution as we seen in the last slide. And this is just to organize things in a neat fashion. We have an input state rho S with some not correlated environment, and it goes through USE, the unitary dynamics, and then we trace over E, and then we get the output of S. But this is not very convenient to write down because every time you need to actually specify what's the environment input state. And then writing the joint unitary might not be the most convenient thing because often the times we just care about the system. In some experiments, this environment maybe never have access to that. So if we need to writing down the states for the environment, that is not necessary because we are not going to be able to measure that E state or change these interactions. So to simplify, we can actually use simplified notation called cross operators. Those are the fact that it doesn't look like a unitary is because we use simplification from the unitary and the trace. We combine things together. So here we can simplify the system, simplify the description in the sense that we can assume the environment state is always pure. And this is always possible because if it's not pure, we can add something to purify it, such that the environment is always a pure state, as long as it's large enough. And once it's a pure state, it's easier to write down these input operations. So again, now sigma E, which is the density operator of the environment, is the pure state density operator. So this is the input state. You have unitary dynamics USE. And now the trace, we can do it in certain bases. So there are many, many bases you can choose. Which one would you choose? You can choose arbitrary one, of course. So therefore, the basis choice degree of freedom gives some degree of freedom of choosing the cross operators. So this is, there's a degree of freedom in choosing cross operators coming from the fact that the trace basis can be arbitrary. But sometimes it's convenient to choose a basis where at least E0 is one of the states. And then you have E1 up to En, or if it's finite number of them. And once you choose this basis, it's just slightly convenient. It doesn't really matter. Then you can write down these operators. Here, you might need a bit of math to actually realize. Here, this is a density operator of S and E. However, here, there's a E, states of E. So you can actually interact or exchange this order of things acting on things. You can single out the system S here, while put all the E part sandwiched on the USE. And this is because rho S only concerns of the system S. It doesn't act on E. So the E part can put together first. And then we can define these cross operators LK, which is EK, USE, and E0.
Okay, yeah,
And
great. I just asked that question. What is happening from first equation to second for E naught to pass through onto the unit theory? Yeah, so that's
right. Yeah, that's a good question. So because this is let's say USE is some operator acting on rho S tensors E0. Let's just look at the, maybe let's look at the whole thing. And because these part are tensor products, so you can think about the order where you actually write this down doesn't really matter. You can say this, you can exchange this, for example, you can exchange S and E. It doesn't really matter. So therefore, you can act the operator on E part first, and then you act it on rho S. So if you really want to see this step by step, we can write more steps. Let's say you can write down rho S some of in some basis. For example, it's eigenbasis. That's simple to write down. And from writing down the eigenbasis, you can explicitly write down these interactions. Rho USE. There's a sum of lambda. So sum of lambda tensors some E0 state and USE. And then you can put the summation outside first. So then essentially USE need to act on lambda and E0, and USE dagger acting on lambda and E0, right? So now I think a unitary acting on a vector, and the vector is a tensor product. So you can, it's a matrix acting on a tensor, and you can sort of deal with sum of index of the tensor contraction first, and then deal with the rest. So that's allowed by mathematics. Okay. Hopefully that answers that question. Right, next slide. So once we have a cross operator, then we want to maybe give some properties of a cross operator, so that when you actually write it down, you can check whether there's a valid quantum channel or not, right? Because channels need to map input states to output states. So if you write down operators LK, it might not be valid quantum channel. So there's some requirement for that. So the requirement for quantum channel is completeness of the basis that you are doing the trace. Completeness relation in the direct notation is sum to the identity. But if you think about a matrix, it just says that identity is one in this basis. So you don't want to miss some of the basis elements in the helper space in the trace, because all the measurements, if you think about trace as a measurement and discard the result, all the measurements are equal possible, or not necessarily equal possible, but all the measurements are possible. So you need to include all. And once you require the completeness by summing over the LK, and then the fact that the LK is just given by this form, you will realize that it has to go to the identity of the system. This can also be seen from the fact that the trace of the output must be 1, right? So trace of n rho s has to be 1, and if you input the cross operator, it's LK, LK rho, LK dagger, okay? And when you do trace, you can always order like trace ABC equals trace BCA. This is one of the basic properties of doing trace. You can move around just the last one or the first one. You can move around. So now you move around. Move, for example, LK dagger LK afterwards. And then sum over K is, you can put it here, and then this is sum over K, right? So trace of the output state is a valid quantum state. It goes to 1, And you're writing some operator, which is the sum here. And this holds for any input state. And we know that any input state has trace row 1. So the only case to guarantee this is always true is that this operator part has to be an identity, so that any valid trace 1 operator put in here still is trace 1. So that also makes sense here. Yeah, and of course, you want this to be a valid quantum state, so it's Hermite conjugate should be itself. This is always guaranteed because the way you construct the cross operator, there's L and L dagger. So N dagger is automatically equals N on the input state. So this is the good thing about having the cross operators. Some of these are just built-in. So then the question also arises, here we just described certain interactions. So for example, if you think about a fiber link, this is maybe one of the link. How about you send it to another link and another link? Right, a quantum network is in general connection of a bunch of fibers. So if you have a quantum channel here, quantum channel there, quantum channel there, how to describe this light photon coming from here, going out from there? Okay, so this part is called concatenation of quantum channels. You act one channel on the other and on the other and on the other. And this can be, for example, can be done in the cross operator level. If you have an n row, which is sum of L row L K, another channel n prime acting on this channel, you just add another summation, maybe L, and there's another set of cross operator for the new channel LK, L prime, and then there's LK, and then row LK dagger L prime dagger. So, and by definition, then this we write it as a concatenation. This is just a new notation we introduce. All right. All right, next slide.
Some scratch.
Let me clear. All right. And yeah, this is many different cases of real quantum channels. For example, you have a fiber, then the input and output is described by quantum channel. Quantum memory stores things. The process of storing things and then becomes more noisy can also be described by noisy channel. Satellite communication to ground, it's also some described by a quantum channel. In all these cases, usually we assume that if the light escapes to maybe the universe, and then the next round you send something, these photons are not coming back. And this is usually is called memoryless channels. If these photons, if there's a reflector, then the lost photons might come back, then this will be modeled by a memory effect, this memory channel as well, but we are not going to include it here. That's another topic. If you're interested, you want to look up some, there's a good review of modern physics paper on memory effect in quantum channels. All right, next slide. And here are some examples of simple quantum channels for qubit or qubit systems. Let's consider a two-level quantum system, for example, a qubit, meaning there's a 0 level, 1 level, and they're described by, there's a quantum state psi, and there's an erasure state. And it's important to note that this erasure state is something outside of this original Hilbert space. If you call the original Hilbert space a 0, 1, this erasure state is orthogonal to both 0 and 1. This is the same case in the classical world where there's an erasure state or erasure label. So then the Hilbert space is actually extended to 3 because of the possible erasure error. And an erasure channel essentially says that there's some probability epsilon that the state just get erased. And then there's probability 1 minus epsilon that the state is not erased. And by property mixture of two scenarios, you get the whole output state, which is a mixed state. For example, single photon qubit encodings. Later, Anthony will cover that part. Photon loss can be modeled as an erasure channel because a photon can be maybe horizontal or vertical polarized, but when it's lost, there's no photon, so it becomes a vacuum state, which is orthogonal with a single photon state with different polarizations. So that's an example.
Hey, Quntao,
Yes.
Can you please put the paper name just mentioned? Is the memory effects, is it an RMP?
Yeah, so let me write it down. The review of modern physics, memory effects in quantum channels. It's by, if I remember correctly, it's by F. Caruso and the others.
Okay, I'm putting it in the chat.
Yeah.
Thank you.
Yeah, it's a pretty nice paper. I mean, the review of modern physics is a long paper, but I believe this first author has a couple of other shorter papers, which if you want to read, it may be easier to actually just grasp what is the memory effect in quantum channels. Okay, if people are interested, I can talk a bit about it. So now we just have one system, one environment, and then there's a unitary. Memory effect says that you need to think about things together. So S1 input, the next input S2, the next input S3, they may need to be considered together. And you might need to consider a big unitary on all of it. So that is the overall model. But in some cases, there's some simplifications possible. The distribution can be slightly easier. Right. Hopefully that answers the question. So now let's continue with the polarizing channel. Okay, the polarizing channel is slightly different from erasure channel. In erasure channel, when there's an error happening, you exactly know, okay, there's an error happened. However, in the polarizing channel, this is not the case. When error happened, it's probabilistically 0 or 1. So you might not be able to even detect that this error happened. So in this case, with probability P, you get a fully mixed state. And a fully mixed state, just to be clear, for cubic system, it's just equal probability of 0 and equal probability of 1. And then if it's not fully mixed, then you can have 1 minus P probability of having the original state. Although it doesn't give you the arrow syndrome, or let's say arrow symbol clearly, but this is actually the common case. So in a lot of cases, when you have fault-tolerant quantum computing and you try to design error correcting codes, sometimes you will take the polarizing channel as the model. Later, we may have time to cover that the polarizing channel is equivalent to applying Pauli X, Pauli Y, Pauli Z, and additive with different probabilities. And therefore it covers all different type of Pauli errors. If you are able to correct against the polarizing channel, that includes all possible Pauli errors in this happening. Of course, the normally codes correct up to a certain weight. So the polarizing channel would include all the different weights, and of course include the part you can correct, also include the part you cannot correct. Right, so these are two simple channels we can describe. All right, next slide.
Hold on 1 second. Someone asked, what is the state in the Hilbert space if there is erasure? Since E doesn't lie in the Hilbert space, is this tensor E? Not quite. You can think about this actually as like a larger 3-level system. So let's say so you can think about it as a larger 3-level system where psi is restricted to 2 levels. And then this erasure state is some 3rd level that, maybe you're not addressing or whatever, but that you can have loss into. So an example is a single photon. The entire Hilbert space is some very large Hilbert space, some Fock space of n photons. we restrict to a single photon. And then there's an orthogonal state, the vacuum state, that would be the erasure state. They're still in the same Hilbert space. It's just that when we look at single photon, we're only looking at a subspace. So it's not necessarily, a different Hilbert space.
Yeah. So for example, if you write down the density operating matrix form, so let's say we define 0, 1 state, and then you need to include a arrow state, and then 0, 1 arrow. So the actual density operator you might need to write down is actually 3 by 3 instead of 2 by 2 because of the arrow state. So this is your input state, maybe A, 1 minus A, B star. And then the erasure part, because of the probably mixing, there's an epsilon in here. That will be the output. And then you multiply this everything of the input by 1 minus epsilon. And this will be the output state. And there's an orthogonal part, which could be arrow. So this is different from here, where everything is still just 2 levels. So you have an input, which is maybe A, 1 minus A, B star. And the output is just mixing 1 portion from identity, right? So there's some number here, some number here, and then sum together. It's just still 2 by 2. So that's the difference. Okay. So as we are talking about the trace process, there's a reverse, which is the purification. So when you have a system S, you include E so that the whole system is pure, and you can do partial trace to get S, or you can do purification to reconstruct as E prime. Similarly here, when you describe a quantum channel, we started with a unitary, right? And then we do trace, we get the cross operator, and then we got this simplified definition of quantum channels, or description of quantum channels. But it's also possible to reverse this process in the sense that given the cross operators, we can always put back any environment so that there's a unitary, you can recover the unitary, and you can find the proper environment state. And this is a unitary satisfying this. This is always possible. In principle, well, you need to construct it, and there were not just one construction, just because different type of environment are equivalent to each other up to some unitary degree of freedom. So the fact that you can have different cross operator representing the same quantum channel, slightly different ones representing the same quantum channel, you can also write down different unitary extensions for the same quantum channel. A version that we usually write down is not the whole unitary, because if you think about this, the environment starts with E0, and then the traces with EK basis. So we care less about the environment. So sometimes we don't necessarily need to write down the whole unitaries. And we write down this so-called isometry extension. It's essentially a lazy version of unitary extension. For example, if you have a cross operator LK for the channels, this is always the way to construct isometry, which directly gets this. It's isometry in the sense that the dimension doesn't, it's not d-dimensional to d-dimensional, but it's slightly different. It's good in the sense that you can also write down this V dagger and doing trace on E to actually represent it. So from here you can see V acts on system S, but output states on S and E. So it's a map from S to SE. So therefore it's not unitary, it's so-called isometry. It's really just a slightly simple way to write down things, because we always write this E as E0. So sometimes it's not necessary to always write this out, and therefore we write rho s, just rho s without the E0. Yeah. Yeah. So if you think about it, unitary extension is a proper interaction between S and E, but this VSE, it's really mapping from S to SE, so there's no environment in this isometric extension. But VSE is usually fine for most analysis. We only need VSE because we don't care about the environment as initial state so much. Right, next slide. So, so we're talking about extensions and purifications. So you might wonder, why is this useful, right? Because if you code, let's say, a classical computer to do simulations, then it might be sufficient to just stay in the level of the system where you write down write down density matrix, and then you act these cross operators else. These cross operators are also matrices acting on it, and it becomes the output state, right? So why bother introducing extra degree of freedom E, or even more, there's ancillars to actually allow some unitary extension or unitary representations. And we are in principle. Is there a question or something?
There was no. I was typing a Q&A question.
Sorry. I see. Okay. So the mouse moving around, this is because Anthony is typing some answers. Okay. Yeah. So so you might wonder, we have cross operators, then we can simulate everything, calculate everything on classical computer. So why don't we need this purification? Well, because this purification is very useful for theoretical calculations, like calculating channel capacities or evaluating a lot of cases, proving channel capacities. You use these purifications very often. So let's do a very simple example without the full introduction to quantum capacity, what it is, but we will just give this example. So let's say you have a system S, and there's a channel phi, so that it maps S to S prime. So in order to simplify our analysis, we introduce environment E, so that this is a unitary extension of the channel, or isometry in a lot of cases. S in general might not be pure state. E we can always choose as a pure state. So therefore, to make everything pure, we also need an ancillar A to purify. So we have a rho S to begin with. We purify it to be maybe phi AS, so it's pure. And then E is already pure. So after the purification, we have the overall input state is some phi AS tensors the E0 state of E. And we have the unitary acting on the whole system becomes E prime, S prime, A prime. And the important part is that the output state is still pure, right? Because you have a unitary and this is identity, so nothing is not pure. The output state, you can represent it as USE tensors identity on A, acting on phi, the initial state of AS tensors E0, E. In this analysis, we usually write this index on the right-hand side to denote which system it acts on, so that it's not confusing. If you get rid of this SEA, then you would be confused. Where does this U act on? And because there's a AS and E state here, and we don't necessarily write everything in the same order. If you look at here, we write SEA, while here we have ASE. So this index is very important to keep track of the evolutions. But this is the new state of E prime, S prime, and A prime. And now everything could be entangled together. It's not possible to separate. It's often not possible to separate them anymore. So though the fact that the whole system is still pure, both ASE in input side and A prime, S prime, E prime is pure, it allows you to simplify a lot of calculations. For example, in quantum capacity, well, We don't have the time to introduce the whole why this is called photonic capacity part, but this is the this is the formula we use to calculate the capacity. S is the Fresnel entropy, and this is a slightly higher level course, so we assume you know Fresnel entropy already. But just to make sure, to remind you, Fresnel entropy is the trace of rho, log rho. Usually we take log 2. This, when you diagonalize it, it goes back to the classical Shannon entropy. In the quantum case, this is called a Fresnel entropy. The calculation usually requires a diagonalization, so it's not that easy. So if you can get simplifications, it's always very useful. This quantum capacity is the maximum of so-called coherent information. So this guy is called coherent information. Coherent information is defined as the difference of entropy of the output state. So if you this is n rho s. So if you think about what does the channel n do, is map s to s prime. So in principle, you can write this entropy of s prime. Okay. Sometimes it's a bit confusing, but when we write s, it's entropy. Sometimes we use h when you have a system s. But hopefully it's not too confusing because we have the bracket in front of it. So in another way, you can write this is the entropy of S prime system minus the entropy of this NC is the so-called complemental channel, which is the map from S to the environment E prime. So this becomes the entropy of E prime. And sometimes we don't want to just write down what is E prime because that will need to write down a full unitary extension. But often the case, we just use the fact that the E prime, S prime, A prime is pure. And therefore, the entropy of E prime is equal to the entropy of A prime, S prime. So therefore, instead of calculating the explicitly what is the environment output state, we can still focus on the system side. We just add an purification to the system. So this quantity, let me just erase some parts so I can have room to write. So again, this is entropy of S prime. This is entropy of A prime, S prime. And because of purity of A prime, S prime, E prime, the entropy of this is equal to entropy of E prime. Oh, initially this is E prime. I get the reversed order. Initially, this is the E prime entropy. And because E prime, S prime, A prime is pure, this is equal to entropy of A prime, S prime. And therefore, the coherent information or the quantum capacity can be equivalently write down as a maximum of rho s, entropy of output rho s prime, which is this, and minus the entropy of A prime S prime. That is the channel tensor's identity acting on the purification of A and S. So here you can see now we don't rely on the environment E to write down this coherent information. Everything is written down in terms of input state rho S and its purification. And this sometimes allow a lot of simplification, improving stuff, and also calculations. Okay. All right, let's go to the next slide. Oops, this is poll number 1.
Yeah, okay, I was muted. Okay, yeah, this is another poll. This is a slightly more involved poll. It's not too complicated. And so consider two erasure channels. We went over them briefly, but recall it here. For some state psi, and remember that psi is orthogonal to epsilon here. The concatenation of two erasure channels is another erasure channel, okay, that we name by this little epsilon 1, 2. And what is the erasure probability? Okay, so given epsilon1, epsilon2, what is the erasure probability? And I'll give a few, let me open the polls, but I'll give a few minutes to, let me open it. Here we go. Yeah. Okay, so the polls are open. I'll give you just a few minutes to, maybe 2 minutes to answer this. The answer is quite intuitive, and there's a hint there. Yeah, we talked about erasure channels. We said that concatenation of two channels is another channel, and so here we have concatenation of two erasure channels. Yeah, you still have about a minute or so left. So if you, I don't know if you can change your results, but you can change results, scribble on a piece of paper really quick to try to you know, tell yourself what the answer is, and we'll see. We'll see in about 45 seconds. Okay, great. I'm in the poll now. Don't really, I'll share the results by this. So the answer is C. So the state either gets two erasure channels, gives you another erasure channel. So that means the state gets either, you can think about photon, either gets transmitted or it gets erased. Transmission probability for the first channel is 1 minus epsilon, right? That just follows from this formula. The transmission probability for the second channel is just this. So that means the total transmission probability, it's really just a product of these probabilities. And then the erasure probability is just 1 minus this. Okay. So basically you have two outcomes. One is it gets transmitted and one it gets erased. And so this is the probability that it gets transmitted. And so the probability that it gets erased is just the negation of the first instance. So that's the answer. Great.
What's the poll result?
Oh,
Let's
actually
take a look.
here, let me go back. Oh, yeah. Yeah, so it's this. So
Okay. Yeah. Yeah.
I mean,
Okay.
B is like reasonable. A, yeah, I mean, so this is a product of channels, so at least it should be a product of somethings, not just some geometric mean. But yeah, the answer is C.
Mhm.
Good.
All right, let's continue.
Yeah.
All right, now that concludes the first part of the basic introduction to quantum channels. And now we are going to focus on one particular type of quantum channels that are really useful for optical communication modeling. And this is so-called the Gaussian bosonic channels. It's bosonic because we care about photons, and photons are bosons. And Gaussian, it's similar to in classical information theory, you learn these white noise channels. You always care about Gaussian distribution because Gaussian allow you to do calculation explicitly. The entropy has explicit formula in the classical case. This is also the case in the quantum. So we care about that. Also, Gaussian also models most of the states you can easily generate in the lab. For example, laser is one of the Gaussian states. Those popular entangled states called Tumor squeeze vacuum states from spontaneous parametric down conversion is also Gaussian state. Thermal noise appears everywhere, is also Gaussian. The most of the optical elements, beam splitters, also Gaussian. Phase shifts also Gaussian. Light propagation also Gaussian. Most of the easy part is Gaussian. Rather, it's very hard to actually engineer good non-Gaussian elements under your control because Gaussian plus non-Gaussian becomes everything, will be universal. So universal computing, which is why computing is harder in some sense. Right, let's continue.
Just to say, in maybe about 20 or so minutes, maybe about 10 slides or so, we'll have a break. So just hold on, about a 10 to 15-minute break. So just hold on with us a little bit more. Okay.
So to introduce what is Gaussian, what is bosonic Gaussian channel, we will still need to build up what is our system under study, right? Previously, we've been using finite dimensional systems, which is easier to write down explicitly as a matrix. So here we need to extend our system to infinite dimensional. So the most simple case would be to consider a harmonic oscillator. So let's begin with that. Harmonic oscillator, you learn the classical harmonic oscillator in classical mechanics, and there you have a trap, and then you have a momentum, v squared, and if you write momentum, it's going to be p squared over 2m. So there's x squared, p squared, and then to quantize it, we quantize p and x so that you have a x hat, p hat squared. And then also we can choose, because we are doing theory for now, we can choose, for example, m equals some unit so that you can write down h bar omega in front. So this is how you can go from xp to this unitless or simplified version of Hamiltonian. There's okay, it's slightly complicated to write down all the transforms. Let's forget about that. It's essentially something like m omega. I wouldn't bother about that. So after the unit transform, we can write down harmonic oscillators as a simple h bar omega over 2 q hat square plus p hat square. And this can be solved in many different ways. One simple way is to define those annihilation and creation operators. Annihilation operator is q plus ip, and creation operator it's dagger, which is q minus ip. And here p and q are canonical position and momentum qualitors. Q and p have the commutation relation that it goes to I. So here we've been choosing h bar equals 1. Otherwise, there's a h bar here. So it's very popular to choose h bar equals 1 to simplify what you need to write down. And often the times you also get rid of omega as well. So everything is unitless in that unit choice. Once you introduce annihilation creation operators, you can solve the eigenstates of this oscillator. There's a 0, 1, and 2, 3. These are so-called number states. You can also write this harmonic oscillator Hamiltonian as the number operator plus some vacuum fluctuation. Or people call this vacuum energy because when there's no occupation, n equals 0, this part would be the energy of the system. And so the eigenstates are the number states. So this is what in the optical system, this is what people call as a photon number state. When you talk about a single photon state, this is the single photon state people mean. And two photon state, this is the two photon state people mean. And here we're not writing out the horizontal or vertical polarizations yet. If you want to include that, then essentially this is two modes. The whole state essentially phi. One is horizontal, one is vertical, is some state. We can write one of the bases, for example, when n is horizontal and m is vertical. So the horizontal mode of the excitation described by harmonic oscillator can have occupating numbers from 0, 1, 2 to infinity. The vertical mode can also have a point number of 0, 1 to infinity. And this is essentially a two-mode system. You have this wave function. But later, Anthony will talk about the single photon subspace. That is meaning that you only care about one state in horizontal tensor, 0 state in vertical, or 0 state in horizontal and 1 photon in vertical. So if this is your subspace, then you're in the single photon subspace of two modes, and you can call this 1 or 0 state. This is 1 state, and then you can have your Hilbert space of a qubit, and then do very interesting computing or communication tasks. But to begin with, we will introduce the general fashion of describing things from modes and use the basis, for example, number state basis. And some basic algebra, which you probably want to just keep in mind. this is used very often, but less often when you deal with Gaussian state because we have better tools to deal with it. So A annihilates an operator, annihilation operator decrease the photon number by 1, and then get a factor in front. A creation operator increase the photon number by 1 and get a factor in front. And when n equals 0, because you have square root of 0 in front, so it essentially just equals 0. That means when you annihilate a vacuum, it becomes nothing. So there's a difference between vacuum and nothing. That's very important. Vacuum has a lot of things in it. It's as a maybe high energy physicists like to think about a vacuum as a tons of quantum fluctuations in it. It's not nothing. Okay, let's go to the next slide. So we follow the previous approach. We start from unitary, then we trace out the environment, then we define bosonic channels. And now we need to have more than one mode, because in order to have a meaningful channel, you need two modes at least. Otherwise, it's a single mode. You cannot really describe everything. So let's just start with n modes. These are all the Q and P operators. We tend to write down a vector of operators X, including everything. And for example, this is the notation you can find in Whitbrook's review. It's Whitbrook and et al., Seth Lloyd, Jeff Shapiro, Nicholas Cerf, and others. There's a review of modern physics paper on Gaussian quantum information. And this is same notation. Some other papers might use the notation where you use Q1, Q2, Q3, etc., and then P1, P2, P3. These are different notations, and the commutation relation will be slightly different. And this so-called this is the metric of the space, which is in this definition of Whitbrook, we have this block diagonal 1 minus 1. In those definitions, you will have a different form. Just be careful with which form you're actually using. And when you read papers, depending on which form, you need to convert between these forms. And the conversion is linear, right? Linear algebra. So unitary is described by e to the I, some generator h. And when we say it's Gaussian, it means h is second order in P and Qs. It involves Q squared, PQ, and P squared, etc. Non-Gaussian means that you have higher order, for example, Q to the third, P to the third. Gaussian unitaries result in linear evolutions. This is very important, and this is linear. It's a different notion than linearity of quantum physics. Quantum physics linearity is more general. Here, linear just means that one quadrature operator under the evolution of Gaussian unitaries become some linear combination of other quadrature operators, let's say omega k, qk plus vk, pk, it's some linear combinations. So quadrature operators stay quadrature operators, which is very useful because you can think about this as a coordinate transform in some sense. If you just start from the classical, multivariable property distribution, if you have such a transform, this means that you are transforming the coordinates in some way, and Gaussian function will still be Gaussian after that, right? So it's very useful. And to see why second order Hamiltonians or generators will allow this role, this will need to be relying on this so-called Hadamard-Lamar. It's something from the Lie algebra. You can Google. There's a Wikipedia page about this kind of formulas. There's a Baker, Kemper, Hofstadter formula, BCH formula related to this. But this one is Hadamard-Lamar, essentially e to the a, b, e to the minus a is b plus commutators. And importantly, if you have a as a second order and b as first order, commutator just gives first order things at most. And then these nested commutators will go to 0 at some level. And therefore, you only have linear combinations of quadrature operators, which is a huge simplification in describing these evolutions of dynamics. Right, next slide.
Okay, 1 second. Someone asked, it's quite a simple question, but I think it's, it's good to, it's a good question. Can we be reminded how modes are defined in this context? So when people say modes, they just generally, it's just a general description and it refers to a mode of oscillation. Okay, so it could be a physical mode. So for example, you could have a trapped ion that's trapped in a potential well, then it has physical modes of oscillation, right? So there's in 3D space, it could oscillate this way or that way in a plane. So that's one mode of oscillation. And so for each mode, so for in the X direction, you'll have Q's and P's, in the Y direction, you'll have Q's and P's. And maybe you have many of these trapped ions in a bunch of different wells. So then you'll have many modes. Could be modes of light in a microwave cavity. So you'll have the fundamental mode where the wavelength is equal, or proportional to the cavity length, or, the wavelength is half the cavity length, et cetera, et cetera. And so it can refer to many modes of oscillation.
Yeah, the modes are essentially different degree of freedom of a system, which are infinite dimensional. And here we choose the bosonic ones. You can also define fermionic modes if you study fermionic systems, and you can build up the theory similar to what we are doing here. It's fairly general, includes optical, microwave, or even mechanical oscillations. You can use this paradigm to study it. Okay. Right. So here, let's begin with examples of Gaussian unitaries. So these are linear mappings from one quadrature operator to compositions of different linear combinations of quadrature operators. The simple case is linear Hamiltonian in the sense that you just have one creation, one annihilation. There's no second polynomial. It's just first order polynomial. This can be equivalently written as a P and Q because if you remember, A is Q plus IP, maybe with a square root 2. Probably it's divided by square root of 2 here. Yeah. Yeah, if you input this e to the IH on annihilation operator A, you can show it's mapped to A plus alpha. So it shifts the mean of creation operators. Equivalently, it shifts the mean of Q and P operators. So X becomes X plus some constant D. So this is why we call it displacement. For example, lasers are produced by some cascade process, and there's this bunch of physics in there. But if you think about it theoretically, you can theoretically produce a laser state, a coherent state from displacing a vacuum. Although in practice, this is not what people implement usually, but this is the way you can produce a coherent state, is displaced vacuum. And if you displace a coherent state, it becomes another coherent state with different phase. We can also define a multi-mode version of this. So displace one mode, displace two modes, display multiple modes. It's essentially a tensor product of displacements. It maps X to some vector version of X plus vector version of displacement amplitudes. More importantly, these displacement operators are so-called orthogonal and complete in the sense that the trace of these two displacement operator is a delta function. And this is, in some sense, analog to Pauli operators. If you learned about operators in finite dimensional, so you know that identity sigma x, sigma y, sigma z forms are complete and orthogonal basis. So any operator A can be decomposed into summations of I and x, y, z. And there's also multi-qubit generalizations. So you have Pauli strings. So any operator A can be decomposed into a probability of different Pauli strings P, and then Pauli strings. And similarly, any operator in principle for multiple modes can be decomposed into a integration of some function of C and displacement operator. So this is what it means by being complete. It's just sometimes this function can be very ill-defined if A is certain operators, but this is in principle a true decomposition, and this can be used to simplify calculations. Next slide.
Yeah, I think we have that on the next slide actually.
Yeah, good. So using this orthogonality to delta function, we can define the characteristic function, which is why we need these displacement operators. Characteristic functions are very useful for quantum optics, and people, in the development of quantum optics, people think about how to represent quantum states that are convenient for measurements, and there's different characteristic functions. There's Hoshimi functions, and there's a Q function, etc. All of these can be connected to these characteristic functions, and these characteristic functions, the motivation here is that this is a complete basis. We can define this decomposition, so we can in principle represent any operators by its characteristic function, and so it's also connected to another important function called Wegener function, which is the so-called quasi-probability. If you have a classical system, you describe multivariable classical random variables by probability distribution, and the Wegener function is the quantum version of that. For certain states, Wegener function can be positive and normalized to 1, just like probability distributions, but for some states, Wegener function can be negative. And interestingly, for all Gaussian states, so-called Gaussian states, we haven't really defined them, but these are Gaussian forms of Wegener functions, and for Gaussian functions, it's always positive. And Wegener function is just the Fourier transform of this characteristic function. The reason is that, there's another motivation you want to define a Fourier transform is that think about what's this displacement operator. They are e to the I, maybe C1Q plus or minus C2P, etc. for the single mode case, right? So on an operator level, this looks very much like a Fourier transform. E to the Q and some number, P some number. So this is like a generalized Fourier transform in some sense. So if you reverse the Fourier transform, it's tentative to try to reconstruct some notion of density operator here, except that when you do the reverse Fourier transform, we switched all x and the psi and epsilon here to those numbers. They are not operators anymore. In the forward transform, this is operators Q and P. In the reverse, x is a number. So what you recovered is some number here instead of an operator. And this is why Wegener function is very much like a density operator in some sense. It's very useful because any state can be described by characteristic function and the Wegener function, and therefore quantum channels, quantum process on quantum states in bosonic systems can be described by transforms on Wegener function, and also you can practically do quantum state tomography to measure Wegener functions, and this is often related to either Q function or P function, which are more closely related to quantum tomography, quantum state tomography by homodyne or heterodyne. Sometimes, yeah. So there's a very nice review article, I think, by
It's Mike.
Mike Raymer, right? So there's a very nice article about RMP, again, review of modern physics, Mike Raymer and the others on this subject about tomography, and Wegener function appeared more than one time there. Okay, let's go to the next slide. Here are some examples of Wegener function for example, these vacuum states, which is very nice Gaussian unit variance in this definition, Gaussian distribution. And this is all positive, so it's just like a Gaussian probability distribution. It's really like probability. However, for some other states, like a number state here, the Wegener function can be negative. And here it's the non-single photon states. And you see these negative dips in the middle. And there's a crossover between positive and negative. And some people propose that the number of times this Wegener function cross with this axis of 0 can be used to describe how non-Gaussian the state is. And there's a whole set of resource theory based on that. Also, another set of resource theory concerns, okay, how much non-Gaussianality there is. And people also use negativity, meaning that how negative the Wegener function is to characterize how non-Gaussian the state is. So there's a lot of usefulness from Wegener function to study different type of resource in quantum information processing. Let's go to the next slide.
Yeah, hold on one. So someone asked a nice question. What is the value of the Wegener function described?
So let's see. Here, actually, it's not directly connected to measurement.
That's right.
For example, if you do heterodyne, it will be some convolution of the Wegener function that gives the measurement outcome distribution. So it's closely related, but not directly that. Yeah, maybe one thing I want to point out is that if you integrate out P or Q direction for a single mode, for example, multimode is also similar. If you integrate out one dimension, then if you look at the margin of this distribution, these are actually just the homodyne measurement, or let's say P measurement in this case, measuring P quadrature, the probability outcome will obey exactly this distribution, P. Okay, let's call it PR, probability. So Wegener function is very much like a joint distribution. Its marginal distribution directly describes the homodyne outcome along that quadrature. So this is the P quadrature direction, but you can project that to any direction, and then there's a corresponding measurement called homodyne measurement that can actually has the exact same statistics. Heterodyne is more like a direct way of measuring Wegener, but because of uncertainty principle, there's always some caveat. There's actually a coarse-grained version of Wegener function can be measured by heterodyne. You can reconstruct it, and there's a lot of research in that summarizing that review of modern physics paper on quantum tomography, which tells you how to reconstruct Wegener function from homodyne measurement statistics, heterodyne measurement statistics, or other measurement, or even photon counting. There's a whole story about that. Okay, next slide.
One last thing. This is I thought this was a good question. I'm gonna I answered it in the chat, but still, are there any naturally occurring non-Gaussian states? So that is a non-Gaussian state that doesn't require quantum engineering, but can be found naturally in the environment. I said one thing that high energy physics is full of this kind of stuff, so non-Gaussian interactions, but there you need some. I mean, those really come out in very high energies. So
yeah, natural nonlinearity. So when people say non-Gaussian, another way people usually say it is nonlinearity in optical components. Naturally, nonlinearity is weak, but there is nonlinearity everywhere. Right? You can observe that current nonlinearity, all the crystals, maybe just normal materials, there's certain level of nonlinearity. They're just weak. So natural nonlinearity is weak. That's why it's hard to do very good nonlinear gates.
okay.
So having characteristic function and Wegener function, and we also defined Gaussian unitary. And Gaussian unitary, as we said, is just a coordinate transform on this X, this Wegener, Q and P space. So we can make it that formal here by looking at how Wegener function, how characteristic function transform and Wegener function transform under application of Gaussian unitaries. So let's say any operator A, if you act this unitary most of the time, this A is just some quantum state rho that we care about. And if you apply some Gaussian unitary on this state rho, you essentially just change coordinates to describe the characteristic functions and then change the phase. And for Wiegand functions, you change the mean and change the coordinates as well. So the interpretation is that Gaussian unitaries just mean linear transform in phase space, which is very simple and very easy. But Gaussian unitary does have quantum effects. You might think that, okay, maybe positive Wiegand functions are just like classical, and therefore there's not much quantum in that. That is not correct. Squeeze state, for example, is a quantum, some non-classical state, and it has, very good use in quantum sensing and other places, and it's a Gaussian state and it's positive in Wiegand function. Okay, let's go to the next slide. Okay, this is just naming some of these coordinate transforms. So phase rotation is generated by number operator. You can verify this. If you have a phase rotation, you act on A, it gives phase rotated A. So in Wiegand space, let's say this is some Wiegand function of the original state. After you apply the phase rotation, it rotates by angle phi. So literally it's a phase rotation in the rotation in the Wiegand space. So this models free propagation of modes, of optical modes. The angle phi will be related to the distance and the wave number. So if you have a ideal fiber from A to B, and if it's lossless fiber that you happen to have, then all the propagation is just described by a phase factor, which is very simple. Next slide. And this is single mode squeezing. It's another coordinate transform, and this is non-trivial coordinate transform in the sense that it's essentially compressing one direction, for example, here, and extending the other direction. So it's a symplectic transform. So the Gaussian, vacuum Gaussian distribution, unit vacuum Gaussian becomes a squeeze state, which is, asymmetric, and then the fluctuations on this direction then becomes much smaller, and therefore it benefits measurements and useful for quantum sensing. Okay, next slide. Yeah, we're going to take a break after we finish this slide. And this is another Gaussian transform which involves two modes, which is why we need to introduce this vector version of operators, of quadrature operators. Here because we just have two modes, we just call it A and B. So this is beam splitter, meaning A and B just interfere on these elements and it becomes A prime, B prime. And usually you might have seen formulas like that. Usually we define eta to be cosine theta squared. But if you start from the Hamiltonian, then the theta is essentially something, the evolution is e to the I theta h. Then you have this mode transforms. So it's a coherent exchange of quanta, for example, photons between the modes. So this is where you can have those Mendel interference, right? You have single photons, then you can produce the probability of 0 photons and 2 photons, and those are non-classical interference patterns. All right, let's have a brief break. How long is the break? Like 15 minutes, I think.
Yeah, 10 or 15.
Yeah, 10 or 15. So let's come back. Now it's almost 40, so let's come back at 52.
Somebody asked why there is no imaginary element. I don't know what is meant by that. Do you mean in the Hamiltonian? No, I don't know what is meant by that.
So Hamiltonian, it's a Hermite.
Yeah, I don't know where they mean. No imaginary element where?
So I suppose it's e to the IHT. Why there's no imaginary h? Because if you have an imaginary part, then it's not going to be a unitary. Right? Unitary is trace preserving. If you have an imaginary part, then it will lead to some decay of probability. So if H has some
Oh,
imaginary
no.
part, no,
Yeah.
not here.
No, he just means in the beam splitter transformation. Okay, good.
Oh,
That's simpler.
yeah, that's a simple case. You could have an imaginary phase. That's like a phase shift a to the I theta a. You could have that as well. This is just a simple case.
Yeah, you could have a yeah. So you could have a phase. It's just it just has to do with the phase. All right.
So we kind of separated phase rotation and the beam splitter. So you could combine them together and call them so-called linear optical transform. Then it's a general transform and also involve complex numbers.
Okay, great. So yeah, we can take a 10, 15 minute break.
Mhm. All right, let's start. Okay, we just finished the beam splitter transform, and let's continue to the next Gaussian unitaries. Okay, now we are doing this so-called two-mode squeezing operations. It's very similar to beam splitters. Beam splitters A, B dagger, and then it's conjugate gate. Here, two-mode squeezing, it's A dagger, B dagger. So at the Hamiltonian level, beam splitter, you can think about annihilate one photon in one of the mode, create another photon in the other mode, and the conjugate is the reverse. While the two-mode squeezing is annihilate photons in both modes or create photons in both modes. So you will see this is very different. Although the operators look similar, but these physics will be entirely different. The two-mode squeezing will be generating the so-called two-mode squeeze state, and they are photon pair states. And in terms of the operators, you can go through this math, and the difference is that there's a A and then there's a B dagger instead of just B, and the B and A dagger. And oftentimes we just write the gain, so-called squeezing gain, the two-mode squeezing as the cos squared, so that we call this A prime and B prime. So equivalently, you can write this as A prime equals square root of G A plus, let's add a hat home, plus square root of G minus 1 B dagger. And B prime equals square root of G B plus square root of G minus 1 A dagger. So you might also recognize these actually models. If you look at one subsystem, this models this amplification as well. So when you amplify these inputs, there's inevitably some noise being mixed in if you think about B as the noise. But let's just begin with introducing the operation on two of the two modes, and which is the two-mode squeezing. Okay, next slide. And non-Gaussian unitaries are based on higher order Hamiltonians. For example, Kerr nonlinearity it will be n actually cubed. So if you write down A daggers, it will be A dagger A, A dagger A. So there were 4 operators. And the cube phase gate has q to the third. So these are all non-Gaussian gates. And as I briefly mentioned, non-Gaussian elements, either non-Gaussian states or non-Gaussian operations, are required for quantum error correction, for torrent quantum computing, etc. So Gaussian states are just the state that have the Wiegand function as a Gaussian. We briefly mentioned just to clarify again. And Gaussian operations are those with generators Hamiltonian, the second order, and equivalently they are coordinate transforms of Wiegand functions. So if you have Gaussian operations acting on Gaussian states only, or let's begin with Gaussian unitaries. If you have Gaussian unitaries on Gaussian states, Gaussian unitary on Gaussian states, and because these are just linear coordinate transforms, and Gaussian states are Gaussian with Wiegand functions, so Wiegand function always stay Gaussian. So it essentially means that Gaussian states under Gaussian unitary goes to other Gaussian states. Okay, let's continue. So now that we introduced the Gaussian unitaries, so similar to the past, we introduced the general quantum channels. When we introduce general Gaussian channels, we introduce these unitaries, and then we trace out one part, then becomes one of the channels. So here's one channel called thermal loss channel, which is essentially the reduced mapping of a beam splitter. So beam splitter is that linear optical transform, coherent interference of two modes that we learned. And the whole operation, it's two lines. But if you just look at one line, let's say, how does A mode go? So A mode becomes A prime, and as part of this linear optical transform, then this part is called a thermal loss channel from A to A prime. This is called a thermal loss channel when the E is in a thermal state, which, for example, can be just an environmental thermal noise, which has this Bose-Einstein distribution and therefore Gaussian. We usually use two parameters to characterize thermal loss channel. One is the thermal noise for the number. For example, the environment has some mean for number NB. This is the average thermal noise being mixed in. On these beam splitters. If you ask what's the average mean thermal for the number being mixed in, then often you want to include the prefactor here, 1 minus eta times NB. This can be calculated because let's calculate the mean for the number of A prime. And this would be exponential value of square root of A plus 1 minus AE dagger, and the square root of A plus 1 minus eta E. And if we expand it out, there's 1 eta, A dagger A, and plus 1 minus eta E dagger E. And there will be two cross terms. However, the cross term is 0. This can be verified by thinking about annihilation operator acting on a thermal state. Thermal state will go to 0. If you have both sides, then it's a 0 because the it's a 0 mean state. So here, then we see the effect of having an E being thermal is that the mean for number is going to have some thermal part mixed into it, and the part being mixed in is 1 minus eta times NB. And this is a very important channel because this models fiber communication, for example, depending on the wavelength. So if it's in the optical domain, meaning the wavelength is like terahertz, the frequency is terahertz, wavelength is maybe 1,000 nanometers, then the natural thermal background is very low. So meaning these NB are much smaller than 1. They are almost 0. So in that case, it becomes a pure loss channel, so-called pure loss channel when NB is 0. And all you have is a beam splitter. Essentially, E becomes a vacuum. That would be a special case of this thermal loss channel. Let's go to the next slide. Okay. We have point number 2.
Great. Okay, so poll number 2, so pure loss channel. So Quntao just mentioned a pure loss channel. It's basically when the environment is unpopulated, it's just vacuum. And so pure loss channel has an operator sum representation that looks like this. This is this Kraus decomposition that we reviewed at the beginning of the course. And with Kraus operators that look a bit complicated, but there's only a few pieces that really matter for this question, particularly this last piece, A to the L. So you can imagine this Kraus operator A, this is an annihilation operator. the big AL annihilates L photons. So that's what the Kraus operators are effectively doing. So here's the question. How many Kraus operators do we need to describe the output state given a single photon input state? So let's say we send a single photon state through this channel. How many of these Kraus operators do we need? We don't need all of them. So that's I didn't put that option here. So that's your first hint. We don't need all of them. And again, focus on the AL term and recall that A annihilates photons, reduces photons and annihilates the vacuum. So let me open up the poll, and I'll give you guys about 2 minutes to answer this. So how many of these guys do we need? And be careful when you answer. It might not be as trivial. It's not trivial, but it might not be as trivial as you expect. Okay, looks like everyone's set in. I'll go ahead and close the poll. And so here's the results, and here's I don't know if you can see them both, results of the poll and the solution. So the answer is you need 2. Okay, you at least need 2. So actually, let me exit out of the polls and explain the answer first. So you need 2, and so that's more than 1. I mean, the first one is just so that would take you, so L equals 1 here. That would annihilate 1 photon, so that takes you from 1 photon to 0 photons. Right. And actually, no, L equals 0. So sorry. Yeah, L equals 0 there. So that actually does nothing. And so it does nothing to your state. So it's like, the state just gets transmitted. So you need at least the L equals 0. And you need the L equals 1 because what that does is that annihilates a photon. Okay, so that takes you to the vacuum state. And for all other L, so L greater than or equal to 2, these annihilation bits, they just annihilate the vacuum and they give you 0. And again, it's because annihilation operator takes you to the vacuum, and then applying one more time, you get 0. So only the first 2 Kraus operators are necessary, the L equals 0, L equals 1. And explicitly, they're written like this. Okay. And I said the question is, I mean, the slide is entitled Pure Loss and Erasure because it turns out that with this description, you can write this channel as an erasure channel. So let me just write that out explicitly. So for a single photon state, I'll just label it row 1. You can write this out like so. Square root eta, row 1 plus 1 minus eta. And then this is the A acting on row 1, A dagger. And this is just the vacuum.
You're missing a square root, left and right.
What am I missing? Oh,
So,
yeah, that's right. Oops. Is that it? Yeah. That should be correct, right?
Yeah.
Yeah. So this is exactly an erasure channel. If you remember from before, the erasure channel takes some state psi to one psi. I think I wrote it or did I write it the other way? I forgot how I wrote the erasure probabilities. It might have been something more like this. I think I wrote it in a different way. Yeah, this is if you recall, the erasure channel looks something like this. And if you look at just a single photon state and pure loss channel, this exactly corresponds to an erasure channel. And the erasure state here is the vacuum. So again, someone asked a question way back when and said, "Oh, is the erasure state in a tensor product Hilbert space?" No, the single photon state and the erasure state are in the same big Hilbert space as the Fock space of the mode, but they're orthogonal states. And so again, you can think about this as just multiple level systems, and these are in different levels. So that's that. And I think most people got that, actually got that question right. So, okay, good. Moving on.
Okay, good. Now we have introduced the thermal loss channel with a special case of field loss channel, which most of the time you're going to deal with that. But there's another class of channel we want to introduce because it describes amplification. So thermal amplifier channel. It's the other kind of unitary that we learned. This is the two-mode squeezing. So this is that two-mode squeezing unitary we learned where this is only one line of it. The other line equivalently is E prime is equal to square root of GE plus G minus 1 A dagger. But if you get rid of this line, you are essentially doing a trace. You don't care about the environment. You only care about the input system. Then it becomes the thermal loss channel instead of the two-mode squeezing unitary. And in our notation, we usually define NB, the noise, being the thermal background noise. Sometimes people define noise to be the noise being mixed in the sense that here A prime dagger E prime, if you do the calculation, you will find it's G, the input for the number plus G minus 1. Note that this is because of E dagger, this becomes E and E dagger, right? And an important thing is that there's a commutation relation where this is equal to 1. So this is equal to G, the input, plus G minus 1, 1 plus the thermal for the number of E mode, which is NB. So if you say how much thermal noise is being mixed in, the mean for number is this. It's different from the thermal loss channel case. There's an extra plus 1 because you are doing amplification. Even when this is vacuum, you are going to have some thermal noise because you don't have perfect cloning. When you amplify it, there's have to be some vacuum noise accompanying it. Okay, so this is the thermal amplifier channel. Let's continue.
Okay, great. Yeah, and just to add on that, yeah, and so when this is vacuum, some people call this a quantum limited amplifier channel. So
right,
this quantum limited amplification.
Yeah, and also there's something called a noise figure in thermal amplifier. Is essentially the noise being mixed in 1 plus NB over the noise that if it's a perfect amplification, meaning that the other is vacuum. So essentially it's 1 plus NB will be, and usually people say it in a log version, I mean dB version, 10 log 10 version, how much additional noise you have compared to just perfect quantum limited version. Let's continue. And there's a special case which is sort of on the edge of, on the border of both thermal loss and thermal amplifier, which is the additive Gaussian noise channel, where if you tune the transmissivity to be 1 in the traditional thermal loss channel, then the noise being mixed in is going to be 1 minus eta NB. All right, and then in the thermal amplifier case, the noise is G minus 1, 1 plus NB. So in both cases, if eta goes to 1, this noise goes to 0. If G goes to 1, this noise goes to 0. The channel becomes identity, right? That's the two class we talk about, where the NB is finite. But there's another class of channel where instead of having a finite thermal bath, it's very large thermal bath. So when eta approaches 1, the multiplication actually goes to a constant. For example, this goes to some number. This goes to some number. This is possible because NB can be huge. I mean, in practice, there's always a finite eta, not exactly 1, and then there's some finite NB, then therefore mixing some noise. But the limit of that channel is called the additive Gaussian noise channel, where the mode just get added plus some constant, and this constant is a Gaussian random variable. And this is the most closely related to this classical correspondence of Gaussian channel that's called the additive white noise and white Gaussian noise channel, AWGN channels. This is standard in classical information theory that you learn more models. This channel capacity is regarding these Gaussian noise channels. And this is the quantum version of that. All right, next slide.
Some paper. Okay.
Okay, so now finally, let's talk about cascaded quantum channels. So we've already mentioned the channels can be cascaded. So one channel after another is essentially this so-called concatenation. So you go through N2 first and then go through N1. That's equivalent to N1 acting on the output of N2. We can cascade, for example, thermal loss channel and talk about what's the equivalent channel this produces. So you can use different ways to find out what is the output state. Easy way, which is always recommended, is that when you deal with Gaussian operations or Gaussian quantum process, always think about the so-called Heisenberg evolution instead of Schrödinger evolution. So think about how operators are mapped to each other. So let's start with a input annihilation operator. After the first beam splitter, it becomes eta 1a plus square root 1 minus eta 1 E1 here. And then we have another channel which takes the a double prime, which is square root of eta 2 a prime, because now a prime is the input to the next channel, plus 1 minus eta 2 E2 here. And if you want to expand that out, this would be eta 1, eta 2 a plus there's a eta 2 multiply 1 minus eta 1 E1 plus square root of 1 minus eta 2 E2. So you might be worried, okay, now we have 3 modes in the output. Previously, when we learned the channels, it's always 2 modes. But you can always define modes as a combination of 2 modes as long as it's physical. So you can equivalently define a mode, let's call it E tilde, which is up to normalization, is combination of E1 plus E2. You just need to verify that this satisfies the commutation relation. And then you can write the channel as eta 1, eta 2, a plus square root of 1 minus eta 1, eta 2, E. However, the E mode will have a non-trivial meaningful number if the original channels have a thermal noise. So E1, E2, if they are thermal state, you can calculate the meaningful number of E, which is the noise of the new channel, the concatenate channel, and then it doesn't take much now to realize the meaningful number just by looking at this expression. Because there's E dagger E, so this square root all disappear, and then E1 dagger E1 becomes N1, the meaningful number of the first channel. E2 dagger E2 becomes the meaningful number of the next channel, and then these combination factors will reside here. And the overall transmissivity, you can also directly recognize here. The first mode A, when its output side gets a eta 1, eta 2 A plus 1 minus eta 1, eta 2 E. So the equivalent transmissivity is eta 1, eta 2. So now you can realize that the concatenation of two thermal loss channel becomes another thermal loss channel, but with different transmissivity and different noise, which is very nice because it's another Gaussian channel we know how to describe. So this is coming from the fact that Gaussian operations on Gaussian states, Gaussian operations plus another Gaussian operations, they are still Gaussian operations. So you do one coordinate transform to another coordinate transform, it's still overall a linear coordinate transform. Okay, let's continue. And similarly, for amplification channels, you can also do concatenation. I will not go through the derivations. It's slightly more involved in the sense that depending on the, okay, here is the first lossy device, thermal loss channel, and then thermal amplifier channel. Depending on whether overall it's the gain is larger than the loss or the gain is smaller than the loss, then the equivalent channel would be additive noise channel if it equals 1, thermal loss channel if it's smaller than 1, thermal noise, thermal amplifier channel if it's greater than 1. And then this equivalent thermal noise level can all be calculated correspondingly. So depending on the values, this could be a amplifier in the end, or this could be a loss in the end, or it could be additive noise in the end. The important takeaway is that now Gaussian channel, concatenate Gaussian channel is still another Gaussian channel, and we know how to describe it. Let's continue.
Okay. I was answering a question. There we go.
Mm-hmm.
Oh, okay.
Yeah, there's a exercise which essentially amplifier than loss is less lossy. So from before we have that there were two ways you can potentially concatenate a loss channel and the amplifier channel. You can have a loss first, so you lost something first and then you amplify, or you amplify first and the loss to a loss. So the question is, which one is better in the terms of the transmission quality? In this case, if we match up this gain amplifier, then the question would be how much additional noise you would have on the output side if the input is a vacuum, right? Lower noise means better quality. So maybe let's start with some intuitive understanding. If something is lost first and then you amplify, it's like you have some defect in the first place and then amplify that defect. So it's likely to be more noisy. While if you amplify first, the thing you're amplifying is something perfect. So there's no defect being amplified. So intuitively, amplify first is always better. That's indeed the case, but you need to prove it. So the way you prove it is to still use these channel concatenations. So if you do, if you have amplify first, then this is the input-output relation, then you do loss. It takes a bit algebra to figure out, but the A2 mode can be calculated. It's slightly non-trivial. And then the noise level can be evaluated. And if you do it the other way around, if you do a loss first, then vacuum is still vacuum, and then amplify, then the noise is simply just G minus 1, right? G minus 1 will be the noise here. Well, in this case, the result is G minus 1 divided by G, and because G is greater than 1, so the amplify first is less lossy. So the takeaway is that the amplifier, you always want to have amplifier first if you want to transmit something, and then amplify. It's less ideal if you amplify the next. And overall, both channels reduce to additive noise channel. There's actually an overall question. If you want to map a loss channel, thermal loss channel to a additive noise channel, not necessarily Gaussian, non-Gaussian is fine. So is there another way you can do it? Some other concatenation, maybe some other channel that can do it. besides this just simple thermal amplifier channel, such that the noise level may be even lower than this. By noise being lower, maybe the variance is actually smaller than the than what you will get from everything Gaussian. If you amplify first and then loss, question is there something else better than amplification you can do so that the channel is still additive noise, but not necessarily Gaussian, but the variance can be lower than this value. If you can find out something like that, it will be very useful for some type of error correction, because if you stand over a fiber, if you want to have a faithful state transfer, you want to make sure that the mean is the same. You send a coherent state alpha, the received state is coherent state alpha plus some noise, and you want to minimize the noise. And therefore, this additive noise is smaller, the better. And also, if you do error correction, then you want to correct away this additive noise. So of course, then you start with the lower noise, then the better you can correct. All right. So there's some open question along this line. Let's continue. Okay. So next part, Anthony will talk about things when we go to a single photon instead of on the modes, and then introduce what is the corresponding channel modeling.
Okay. Great. So now Quntao gets break, and I'll finish us off here. About single photons. So a lot of communication, linear optical, quantum information processing, things like that are done with single photons. For example, single photon qubits and things of this nature. And so we'll talk about the sort of encoding a qubit into a photon, degrees of freedom, and some poly operations on that single photon qubits. Okay, so just to start off, so a dual rail qubit. This will be a photon encoding, so encoding a qubit into a photon. So photons have many degrees of freedom, right? So we have, maybe polarization, spatial, angular momentum, things like that. So if I can just draw some pictures. So polarization, right? We have two orthogonal polarization directions associated with the polarization of the photon, either horizontal or vertical, or some other basis. We have that. We have spatial. So for spatial, you can think about literally different spatial modes, like spatially separated and confined beams. So an example of that would be some linear optical, circuit. So this is polarization. This is spatial. And there's other ones, et cetera, et cetera. Like there's, you can talk about the actual spatial profile. So, and have modes with different angular momentum. So these are angular momentum modes, and things of that sort. And so each of these degrees of freedom are described by a set of mode operators. So just like we introduced modes before, we have a set of annihilation operators, A hat K, and M is the number of these orthogonal modes in this set. So for the polarization, there's two orthogonal modes, that's V and H. For spatial, it's just however many, sort of lines in the circuit you have, etc. So we'll generally focus on two modes. So K equals 1 and 2. So you just have two modes, and to define a photonic qubit. And so in this way, we'll define these logical states, these qubit states, as single photon states. Okay, so the logical 0 is you have a photon in the first mode. Logical 1 is you have a photon in the second mode. Okay, so for horizontal or vertical, it's maybe you have the logical 0 is you have a horizontal polarization, horizontally polarized photon, and the 1 might be you have a vertically polarized photon. Okay, and so this is a dual rail qubit. Could also be a spatial qubit. So you could have a photon in the first spatial mode, or a photon in the second spatial mode. Okay, and just to stress here, I'm writing it in this simplified fashion, but technically, in this case, we're always dealing with two modes. And so this is really a product of Hilbert spaces. Okay. So when I write A1 dagger on the vacuum, what I really mean is that the A1 dagger is acting on the first mode, and then nothing's happening on the second mode. Okay, so that's an example of dual rail qubit. So a very general description. So single qubit operations in this dual railed encoding can actually be done with so-called passive operations. And what I mean by that is the passive operations commute with the total photon number. Okay. And where the photon number is just the sum of the sum of the number of photons in the different modes. So here, this is the total photon number, and this is the photon number in each mode. And you know, these passive operations consist quite generically. Again, you can think about them as in vertical or horizontal polarization, or in spatial modes, and they just consist of unitary beam splitters and phase shifters. So the beam splitters have this generic form. This is what Quntao was that we looked at before. So this would be this would correspond to, you know, cosine theta, like a beam splitter with transmission probability cosine squared theta. And this would be this phase. Someone mentioned a phase previously, like why wasn't there an I phase in some beam splitter transformation? You can include that with this general description. Then the phase shifts, again, this is like just free propagation. So you have an in hat for the mode and the phase that gets induced on the mode. So if these are different spatial modes, for example, you know, you would have a physical beam splitter, and then, you know, a phase maybe is that was a poor drawing. You know, maybe this phase, you literally just propagate one mode along a fiber that's wound up, and you can induce a phase in that manner. Okay. So here's an exercise. I mentioned earlier that passive transformations or passive operations commute with a total photon number. So they preserve the total number of photons between the modes. And so quite generically, you can write any passive operation in this form. It has a Hamiltonian that looks like this. Okay, where these Hij's, they have all these thetas and phis and such in them. Okay, so these are complex numbers. So you can write any passive operation between two modes and in this way. And so the goal is to show that H hat above commutes with N hat. And so therefore preserves total photon number. So what does this mean just physically, by the way, preserves total photon number? This just means that no photons are lost out of their system. They're just sort of exchanged between the modes. So some photons can go to the first, some photons can go to the second, vice versa. And to do this, it's really just equivalent to show that this commutator right here is equal to 0. And that's quite easy to do. And actually, we'll just forget about this sum and just do this first part, just to show that. And so let's do that. Let's do this. Actually, no, I will have the sum in there. So we'll use these little trick right here to do that. This, or it's not a trick, but is use this identity and do the following. Okay, AK. I'm gonna not write hats for brevity. So because there's so many indices and stuff like that. Just everything that I'm writing right now should technically have hats. So just keep that in mind. AJ. So what is this equal to? Yeah. So we're going to pull these first bits out using this identity, this exclamation mark above. Dagger AJ plus K dagger, J. Okay. Okay. So that's the first use of the identity. We're going to use this identity again, but now I'm going to skip one small step and just write it in the margins here. We're going to also use the fact that that the annihilation operators all commute for all I mean I could equal K, but the annihilation operators commute. Okay. So I'm going to use that to just skip one step. Oops. Yeah, let me keep writing in red here. What red was I using before? Okay, anyways. So AK dagger. And so this can be written as AK, AI dagger, AJ. This is using this step in blue here that I just wrote down. Basically, I'm using this identity and then throwing out one of the terms because of this. Okay. Plus AK, oops, let me divide it this way. Plus AI dagger, AK dagger, AJ, AK. Okay. Now we use this commutation relation up here. Right. So this will be AK dagger minus delta KI AJ plus AI dagger. Guess I don't need that. Delta KJ AK. Right. And so what is that equal to? J plus AI dagger AJ, and then we see that this is this vanishes, so this is equal to 0. So inputting this equation back into here or somewhere, where is it? Yeah, inputting this commutator back into here, so that implies that that's equal to 0. So passive operations conserve the total photon number. They just kind of move stuff around. And so these single qubit operations, they just kind of shift quanta back and forth and then do these phase rotations. Okay, great. So the beam splitter transformation, yeah, so this is a 2-mode transformation. We saw this before. I'll write it here just slightly differently in this sort of matrix form. And so here's just an example of a logical 0 state. So we'll define the logical 0 state as a photon being in the first mode and not in the second. And then we can actually make a qubit state in the following way. So some qubit state psi by this generalized beam splitter. Okay. So the action of the beam splitter on the modes is this. Okay, so you have some cosine thetas and some phases. And if you work these creation and annihilation operators out, you'll get something of this form. Okay, and you can create this kind of thing with a Mach-Zehnder type of interferometer. So actually, you can generate this with instead of using this sort of abstract representation, you can actually generate this with a Mach-Zehnder interferometer. I think there's some phases somewhere, thetas. There's a phi within the interferometer and there's a theta outside, and these are 50-50 beam splitters, both of these. So you can generate this kind of transformation with a Mach-Zehnder interferometer. And so in this way, you can transform states like from 0 to this state and a logical 1 to this state, and etc. So you can perform sort of these qubit rotations in this fashion. Okay. Great. So pole. So these are qubit operations, single qubit operations using this. And so here's a nice little interesting question. Poly X with a beam splitter. So we can here's a question. Can we implement a poly X transformation? So like this would induce a bit flip. So just recall. So poly X operation acting on a 0 state, it's a bit flip, so it takes it to a 1, and from a 1 to a 0 state. Okay. And so the question is, up to a global phase, let's ignore global phases, can we implement poly X matrix X? And actually this beam splitter will, just be something of this form right here, a poly X. It'll look basically like this up to some constant out front. So that's the question. And so let me open the polls. Yeah. So I'll give you about 2 minutes to answer that question. So the question again is, can we implement a poly X? And if so, maybe you can write out what the thetas need to be in order to do that. Thetas and phis. Phi needs to take on a certain value as well. So simple question is yes or no, and then slightly more complicated question is, what are the theta and phis that you need to be able to implement a poly X? If so. Okay, great. In poll. And so here's the results just quickly. So about 83% of you said yes, and that is the correct answer. So how do we do that? Yes, so you can implement a poly X with this. It's actually straightforward. You can just choose theta phi equals pi half and substitute into this matrix above. And what you'll find is that you get something like this. Okay, so that's equivalent to a poly X up to an overall phase of e to the pi over 2. So up to, and this is of course, this is just equal to I. Okay, so this is equivalent to I poly X. Yeah, so that's equivalent to an I times poly X. There's somehow pole is not appearing. Okay. Yeah, I'm not sure why. A lot of people answer the polls. I'm not sure why the poll is not appearing. Sorry, anonymous attendee. Can you do these quantum? I don't know. Maybe that's a good question. Can you do these quantum computation tasks like rotations with coherent states instead of single photons, encoding the qubit in the polarization of a coherent state? Those states are not actually orthogonal, and maybe this is a roundabout answer. You certainly cannot do quantum computations with coherent states or universal quantum computations with coherent states, because coherent states are Gaussian states. You need non-Gaussian elements somewhere. So it's a good question with coherent states instead of single photon states. First of all, if you try to do something like that, even at the elementary level, those coherent states wouldn't be orthogonal. So if you try to define qubit, this sort of dual rail encoding in the same way, it turns out that those logical states would not be orthogonal. Unless alpha was very, very large. So the coherent state, the population was extremely large. So that's the first hurdle. And I'm sure there's more. Yeah. Okay. Yeah, so most of the time when people, so talk about dual rail encoding, they generally mean single photon state and then in 2 different modes. People do other kind of things as well. So for example, people do this like Fock encoding, or this number state encoding, where they do like a 0 state is the vacuum, and then the first excited state, a single photon state, is the logical 1. It's just in those cases, things a little bit different. Now the Pauli operations become quite difficult because now you have to transition between 0 photons and 1 photon in like coherent fashion. And so this is probably one of the simplest types of encodings, this dual rail qubit. It's also useful for in many quantum communication tasks, like practically useful. Okay, so here's another question. It's really an exercise, and just to go over some of this. By the way, I just want to mention, I don't know if you mentioned this before, but it should have been shared to you guys a set of lecture notes that are typed that have all of these exercises within them, and also a bit more detailed notes. It doesn't have all the pretty pictures, unfortunately. Perhaps you can draw your own, but a lot of these stuff is also in the lecture notes. So hopefully those were shared with you. Anyway, so here's another exercise. Talk about a Hadamard matrix, which is a useful single qubit operation as well. Basically, switches Hadamard matrix kind of switches between the X and Z basis states. And so consider transformation matrices for phase shifts and beam splitters, so you can write them in this fashion. And so a question is, what combination of phase shifters and beam splitters produces a Hadamard matrix? It turns out that you need both. And so you can choose, turns out you can generate a Hadamard with an appropriate combination of these phase shifts and the beam splitters. And one possible way is to choose the phases in this way, so that your phase matrix is basically like a poly Z, and then choose the thetas in the beam splitter. And so you have a 50-50 beam splitter here with pi half rotation, such that the beam splitter looks like this. Okay, so this is actually just a generic kind of like 50-50 beam splitter that Quntao wrote out before. And then what you have after doing that is the combination of this is precisely a Hadamard matrix. And so that's pretty simple to show. And I'll just show that real quickly, just for the sake of doing so, that 1, 0, 0, minus 1, 1, minus 1, 1, 1 is equal to, so what is that? 1, 1, 1 minus 1. And yeah, that's proportional to Hadamard. And it's actually equivalent up to this factor of 1 over square root of 2 that I didn't write out explicitly. Okay, so great. So yeah, you can do Pauli X's, Pauli Z's, and Hadamard transformations. So then you'll get a lot of good stuff there. So precisely this Pauli Z is just the phase rotation. Okay, lecture notes were linked in the Zoom reminder. You can also find them here. Okay, so thanks, Brianna. So lecture notes are a link to them is also in the chat, as well as the slides. Okay, great. So spatial polarization and time band encoding. So these are 3 different types of encodings that are very common for photonic quantum information processing, either for communication or for quantum computation. And so when choosing photonic degree of freedom for encoding, so spatial polarization and time band, it usually depends on the task that you want to do. And so you might have some questions to consider. First of all, depending on your task, is the degree of freedom easy to manipulate? Okay, so for example, doing spatial polarization, you do like physical beam splitters, physical changes in path lengths to implement these phase rotations, etc. For polarization, you need different types of polarizing materials and to do things there. Oops. And then for time band encoding, that's a different thing. So also you need to ask yourself, is the degree of freedom robust to relevant noise sources? You can have various noise sources in the time domain, or there might be some polarization noise or things like that. One thing I will say though is that a photon's a photon, so all of these type of encodings are susceptible to photon loss. So that's just generically how that goes, irrelevant of the type of encoding. and generally it acts on these types of encodings in the same fashion. Another that you might question that you might want to ask yourself is that if necessary and in the future, can we scale up these types of encodings for large-scale quantum information processing with many photons? So, for example, if you're doing spatial encoding, then as you increase the number of modes, then the physical size of the system gets larger, right? You need more if you're for these linear optical quantum information processors. Basically, you need more ports in your interferometer, so the physical size becomes you need a larger size. And again, these questions depend on the context. So these common encodings, for example, spatial. So you can imagine a photon with a fixed frequency, fixed polarization. So a photon has, maybe it's horizontally polarized. That doesn't change. Frequency is the same. But may traverse two distinct paths, right? So you can either have it go down one path or another. And then so you interact photons that go down one path or another by physical beam splitters, right? So these coded mirrors that are connected that connect these two paths, and phase shifts via path links, right? So just the length of a path. So if LK is the length of the top path, if L1 is the length of the top path, L2 is the length of the bottom path, you can introduce phase shifts by making these path links differ. Okay. Polarization. So again, fixed frequency, fixed spatial path, but now it could be a superposition of polarization states. So this is a very common encoding for all photonic quantum communication. For example, I know in these satellite quantum communication demonstrations, people are generally look at these horizontal and vertical modes. You need to find logical states in this way. I mentioned these before. And in this case, you need these birefringent materials to implement single photon operations. So these sort of act on H and V in different manners. That's what these birefringent materials do. There's some questions that Paul, I'll answer them in just one second. Let me get to this time bin. So there's also something called a time bin encoding, which these are kind of interesting. So let me draw a picture. So now we imagine a photon with fixed frequency, polarization, and spatial path, but may occupy two distinct time bin intervals. So you can imagine a photon going over a physical fiber, right? But now you don't know whether it'll arrive. So let's say it arrives at a certain time, but you don't know whether that time will be later or earlier. So it's in a superposition of arriving at one time or a different time, and you don't know which. And so those are kind of cool. So to do those, however, to do like single photon operations, you need fast optical switches, that can, especially if these are if the TL minus TE is quite small, you need these optical switches to be pretty fast. So you need optical switches and delays to implement a single photon operation. So the physical implementation of these beam splitters and phase shifters also will depend on the physical context. Okay. So let me answer some of these questions. It means that we can create any gate with phase shift and beam splitters. What about T-gate? That's a good question. Let me ask my esteemed colleague. Hey, Quntao, are you there?
Yes, I'm here.
Do you know if you can implement a T-gate with beam splitters and phase shifts?
Oh, that's for single photons, right?
Yeah, I think so.
Probably yes.
You certainly won't. Well, let me say this. I don't know about phase shifts and beam splitters. Whatever it is, I don't know. You might need something else, but it will have to commute with total photon number. That's for sure. What about T-gate?
So I know in all you need to do for universal computing is having single photons and beam splitters, phase shifters, and then photon counting. So has to be a way to implement it, right?
Yeah, so maybe I'll say, not off the top of my head, but I'll say CRMP by Dowling et al. I don't think John Dowling is the first author, but he was my advisor, and I know he's on the RMP. linear optical quantum computing. They probably have something to say about it there. So that's my sort of get out way to answer that question. So, okay, I'm a bit confused. How do we apply beam splitter on the two modes of photons when it is encoded in polarization? Should it first go through a polarizing beam splitter? So yeah, you use polarizing beam splitters and birefringent materials. Which of these degrees of freedom is more difficult to calibrate? For instance, if I want photons to be indistinguishable so that all of these are the same for all photons. I don't know. I don't know. Thankfully, I'm a theorist, so I don't have to do any of these calibrations. I know, I mean, the most common, at least for, depends on your task, but I know for like a bunch of sort of, people looking at quantum computation with linear optical quantum computing, like psi-quantum and things like that, they work with spatial modes, right? But people also work with horizontal and vertical polarization modes. So I think that probably depends on the context. Are mixed encodings possible as a means of qubit scaling? For example, time bend plus polarization plus spatial. So this would be like that's like almost like multiplexing or close to something like using sort of hyper entanglement or things like that. Certainly possible. I don't know if that's a common thing to do, is to use multiple degrees of freedom simultaneously for scaling. Yeah, it's a good question. But generally, when people like, for example, when people look at linear optical photonic quantum computing, they do look at spatial. I think there's some where people mix space and time, and so yeah, encoding in spatial and time bend modes. So it's certainly possible. And then anonymous attendee said, yes, we can implement T-gates. We can implement any use of universal single qubit operation using a beam splitter. So you can either take anonymous attendees' word for it, or you can go through some calculations to try to see if you can. But I think he is right. I think you should be able to. Okay. Let me delete that and move on. So one thing you can do is you can also swap between encodings, and this, you can maybe also think of this as a route to doing. So maybe you have one encoding that you can do simple operations on, but maybe it's useful to do another encoding for something else. And so you can swap between encodings to actually do operations and then swap back and do things of this nature. So for example, given two polarization modes and two spatial modes 1 and 2, you can implement a polarizing beam splitter. So someone mentioned a polarizing beam splitter that does the following. So if you have, AH1, so this is a photon with H polarization in the first spatial mode. So physically it corresponds to this. So AH1, it maps it to AH1. So it just goes right through this beam splitter. If you have AH2, so a photon in this mode, again, it just transmits right through. However, due to the polarizing nature of the material, if you have a vertical mode, it gets reflected. So if you have a vertical mode here, it gets reflected. And then again, if you have a vertical mode here, it gets reflected. And yeah, so you can actually use that to, this is actually a typo. I think this is supposed to be, yeah. So if you think about these as like A V2 prime, it's actually just the AV1 inputs. So this gives you a way to actually map, sort of collect all the, yeah, this actually gives you a map, a way to swap between polarization and qubit. Yeah, I'm not gonna go through this, but I think it's just useful to know. And so you can actually follow up with polarizing rotations, polarization rotations, to make this mapping complete. And there's some details in this very nice book, Optical Quantum Information Processing by Peter Koch and Levitt. Okay. Let me move on here. So single photon evolution. So we talked about encoding and degrees of freedom. And Quntao before talked about channels and channel evolution. So it's natural to ask, okay, well, if we have single photon, you know, a qubit encoded into a single photon, and we send it through a channel, how does that evolve? Okay. And perhaps the most prominent noise channel that one should consider is for photons, like in general, it always goes back to this thermal loss channel. So all communication links, i.e. quantum channels, are over like noisy fibers or free space. Could also be a damped resonator mode. And all of these can be modeled by to a very high degree by thermal loss channels. Okay, and so what we'll focus on is thermal loss channel on a single photon state, row 1, right here at least. Also talk about amplifier a little bit. And so the background quanta in this case, this NB that comes in, it could be, you know, it's population from the environment. It could be from the sun or background lights for free space links, or some scattering effects in the fiber. And then, so the loss probability in this case, the 1 minus eta, is you can think about it, at least for, you know, for like going through a medium or fiber, is actually equal to the absorption probability of the medium. Okay, so for example, given a fiber of length L, this eta is related to L in this manner, where alpha is an attenuation coefficient. And this is just characteristic of any sort of simple medium, that you have exponential attenuation as a consequence of this, like it's like a Beer-Lambert law. Okay, so you have you know, the medium consists of atoms, molecules, and such, and they can absorb photons and then re-emit them as you know, sort of different kinds of quanta, maybe infrared quanta and stuff like that. And so this typically leads to exponential loss. You can have it in free space as well, except for in that case, the loss isn't quite just due to this this kind of thing. Actually, I'll draw a picture real quick in that case, because the loss in free space case is actually a bit different. In the free space case, what you generally have is, I'll take the sort of extreme example of a satellite. So, for example, this Mozi satellite, this Chinese satellite, Mozi, that does all these quantum teleportation experiments. What they'll generally do is they'll send photons in space to some station on the ground that then picks them up with a telescope. And now the photons from space, they have some Gaussian profile which expands as it goes from the satellite to the ground. And a single photon in this Gaussian profile has some probability to be at any of these, you know, sort of if you think about putting detectors in this beam width, it's a probability to be in any of these locations in the beam width. And unfortunately, you know, we do not have optical ground stations with telescopes that are kilometers in size. And so it only actually picks up like a portion of this spread Gaussian beam. And so the dominant amount of loss from these sort of, in this very extreme case, from free space propagation is actually due to collection efficiency. And it's typically, it goes something like this distance squared over A, where A is the size of this receiver. And so that's what dominates the loss budget and these in free space links. Okay. Right. And so thermal loss channel decomposition.
So whenever you have thermal loss, again, you have loss plus some noisy photons. It turns out that you can write this in a very nice way, which is useful in several different contexts. Turns out that a thermal loss channel is actually just a concatenation of a pure loss channel, so no photons added, and then amplification. And the parameters are given in this manner. And this is quite easy to show. And again, it just uses the same techniques. So if you have this, so we'll define these sort of operations here. And AG0 takes A prime to A double prime. And so we can write A prime from before. We have this. Oops. A plus 1 minus tau E1. Now, because this is a pure loss channel, NB equals 0, E1 dagger, E1 is actually 0. Okay, so it's in a vacuum state. And A double prime is equal to, so this is sending A prime through an amplifier. A prime plus G minus 1 E2 dagger. So now, again, E2 dagger E2. This is a pure quantum limited amplifier. So it adds at least this much zero thermal noise. It'll add amplifier noise, but it adds zero thermal noise. And you can expand this out. Again, this is still using the same techniques that Quntao went over. We always do it in this way. It's very simple. G 1 minus tau square root E1 plus G minus 1 E2 dagger. And you can define modes, G tau A prime plus 1 minus G tau. What did I call it? Maybe I called it E1 2 because it's a combination of 1 and 2, which is some combination of these modes here. Okay, and then what you have also is you have E1 2 dagger, E1 2 is then equal to G minus 1 over 1 minus G tau. Okay, and that's this photon number up top. And yeah, note that this depends on G. So if G is 1, if there is no amplifier, then there is no added photons. So this noise is really coming from this the amplifier noise in this channel concatenation.
Yeah, so there's a question. The channels are now acting over the operators instead of the states. You can think of this as you do unit.
I write it in this way for simplicity. I write it in this manner for simplicity. At the end of the day, what this really is that this is a beam splitter. This is a beam splitter, and this is a two-mode squeezer. And so this is a beam splitter transformation.
I'm just ignoring the E1 mode.
This is an amplifier. I mean, this is a two-mode squeezer.
I'm just ignoring the E2 mode. Okay. And so you can think about it in that manner, is that's what's happening. It's really a unitary from A to, so it's a Heisenberg picture, unitary evolution from A to A prime. And of course, there's this E1 mode here. It's just that when I do the final thing, I'm ignoring that. I'm sort of throwing out these E1s, E2s, etc.
So this is really a Heisenberg picture, and there's other evolutions here, right? There's E1 prime and there's E2 prime. I'm just not including those. And so this sort of channel way of taking A to A prime, that's more so me being maybe lazy. Hopefully that answers your question. Okay. Great. Here's a bunch of mess. So these things also have these Kraus decompositions. These Kraus operators, we mentioned this pure loss channel from before. Again, if you want to really look at single photon evolution through a thermal loss channel, you need to calculate things properly, because maybe you send a single photon through a thermal loss channel and a photon goes, maybe you end up detecting a photon at the end. So let me write this down, because I think this is a lot of math that looks right here, but this is why it's important. So let's say you have a fiber, you send something in, and this is in row, and then you detect. Okay, click, you detect. And so then there's a question. Did I detect my photon, the photon I wanted to send, so row, or did I detect some noise photon which has nothing, doesn't even contain my signal? Okay, and to answer that question, you need to go through and at least theoretically, you need to go through and calculate these things. And so this is where this Kraus representation is helpful. And so that's what we'll look at briefly, is calculating the probabilities of transmitting a single photon through a thermal loss channel, like a thermal lossy environment. Okay. And so these are the Kraus operators for this. If I just say them intuitively what they are, again, thermal loss is like the AL is like I'm losing AL photons. The quantum limited amplifier, it's sort of the reverse of that. It's quite different. Ignore this prefactor. That'll just give you basically some constant. What matters is here the amplifier is that I'm gaining k photons. So I'm adding k photons to the state. And then the joint channel, it can be written as it's just this concatenation, but in terms of Kraus operators, it's both of these possibilities happening. So I'm losing photons, but I'm also sort of gaining photons. And the photons that I'm gaining are from the environment. Okay. Right. So single photon input. So we want to look at the output. Okay. So remember from an exercise before, so we'll take this one step at a time. So remember from an exercise before, I think it was a poll before, right? So this is if you recall up here, this is the Kraus decomposition for a thermal loss channel. Let's take this one step at a time. Let's just look at the ALs. So how many of these AL terms do we need? From before, we only need 2 of these in this sum, the L equals 0 and L equals 1. And so for L equals 0, it's just saying, oh, well, I just transmitted my photon with probability tau. You can think of it that way. I transmitted my photon, rho 1, with probability tau. Or I just destroyed my photon and I'm left with vacuum with probability 1 minus tau. Okay, and so that's it. However, given this state, these outcomes will then go into the next level, which is this amplifier. And so then we'll get some extra bits due to this amplifier noise. Okay. I think I've already answered this poll. So hopefully for people that were listening, this should be quite easy to answer. I think I answered this a while back. So when acting on a single photon state, the pure loss channel is equivalent to an erasure channel with erasure probability epsilon equals 1 minus tau. What is the erasure state in this case? Okay, so recall uh, erasure goes like this. where this erasure state is orthogonal to the subspace that rho is in. Okay, so for a single photon, given a single photon, what is the erasure state in this case? Okay, so let me open up the polls. This is the final poll question, by the way. So get in your poll question now if you haven't before. And so I'll just give you like 1 minute to answer this. Okay, so let me end the poll and just share the results. So yeah, the most people got this correct. Yeah, the erasure state in this case is just the vacuum state. And so where are you? Let me get out of this poll. So yeah, explicitly you write the loss channel in this way. So tau with some probability you get the photon, and then with some probability you just get the vacuum. Okay, so for the pure loss channel, there's no mixing of other photons happening. There is no like weird things happening in the space. The completely mixed single photon state, that would be like if you have you don't lose a photon, but the state of it is completely wobbled. Okay, so it's somehow a coherent, I mean, an incoherent mixture of an H and a V. Okay. So let's continue with this other example. So for thermal loss, so we went over the first part, which is this bit here. The photon loss was pretty simple. It's because only like a few outcomes that you can have. Okay, you can have like loss, and then you can have, you lose a single photon, or nothing happens and you keep the photon, and that's about it. For the amplifier channel, it's a little more complicated because now we're adding photons and we can go all the way up with this ladder of the Fock space. But in this case, we'll just stick to a few of these guys, and the relevant operators are just the first few. So the 0 is just this operator. This is basically what you're doing is multiplying by constant. And the second operator is this, and what you're doing is adding a photon. And the reason we're just sticking to these is we're assuming that, maybe this thermal noise, this amplifier noise is quite small. Because if it's large, then, I'm adding tons and tons of photons. Okay, so we're assuming this noise is quite small so that at least with high probability, it only adds like maybe a single photon. And so if you append these guys and do this expansion, there are many possible outcomes. So I'll just go through them one by one. So right here, this is like nothing happens. Okay. Okay. So for A naught, you just get, means you're getting transmitted, and B naught, again, that just means you're getting nothing's happening to your state. No photons are added. So in this case, the photon is unaffected by the channel. Okay. The second case, you don't lose the photon, but a photon gets added to your channel. So there's one noisy photon added to the state. So you have this rho 2 here is your original single photon state, but now you apply a creation operator on it, and you've added one noisy photon from the environment. And this noisy photon, I mean, it's an incoherent photon. It's a thermal photon. Okay. There's another possibility. So here, it's you lose a photon, but there's no amplification. Okay. So in that case, the photon's just lost, and that's it. Right. And the third possibility, and so this actually goes back to this this completely mixed state from the previous question. So let's say I lose the photon, but then I add a photon from the environment. Okay. In this case, the photon is lost, but then it's replaced with a single noisy photon state, theta 1. So for a completely mixed photonic qubit, this would just be the identity. Okay. There are some questions. Seems like a missing dagger on the last B in the product. Yes, there is. Thank you. Let me actually go ahead and write that down in my notes. Oh, and all of them. Yeah, nice catch. Thank you. Yeah, and all of these 1 through 4. There's a missing B daggers.
So these should all have B daggers on those. Thank you. Could you elaborate on how to determine whether a detected photon is really your signal photon or noise photon, or do you have suggested references on this? I mean, I don't think you can, right? I mean, yeah, I don't think you can. You can try to do some filtering process to reduce the number of added photons, but I mean, yeah. And so, for example, if you know that you're looking for a photon with a particular spatial, so let's say you don't know whether it's horizontal or vertical, so you're not going to do a filter there. So let's say you have a polarization qubit. You don't know whether it's horizontal or vertical, so you're not going to do any filtering there. But you know that it has a particular spatial profile, or that it's supposed to arrive within a particular time bin. Okay, and it has a particular frequency, very tightly narrowed. So those can all be now filters so that you can filter out other possible noise sources. So you can do a frequency filter where so maybe you just let through just a sliver of photons within a certain frequency range. Maybe you only open your detector for a certain time window when the photon's supposed to arrive. Maybe you only have a certain spatial filter like a fiber or something because you know it's coming in a Gaussian beam. So you can filter it, but I mean, at the end of the day, you're measuring photon. And so whether it's, that'll just be a part of your state, whether it gets mixed or not. So you want to try to reduce the amount of noise as much as possible. But we're trying to communicate like quantum coherence here. And so there is, other than filtering, yeah. Okay, good. And so overall, the state is, you can write it something like this. Okay, so this is a combination of things from before. So this first bit is just successfully transmitted your photon through this lossy, noisy environment. The second part is you get a photon. So this is the kind of related to the question that you just asked. You get a photon, but it's a complete no, it doesn't hold any signal. It doesn't hold any signal whatsoever. Okay. So maybe you can do some filtering process to, that maps the row one really well through the filter, but degrades the theta one. Another possibility is this: you just don't get anything, right? The thing was lost. And finally, the last thing is that you get greater than 2 photons. It's basically just the sum of 1 minus the sum of all of these possibilities. That's what this guy up here is. And so you can think about transmission event probability. So this is the, what is the probability that I actually successfully sent my thing through and detected like the proper photon, not just nothing or a random photon or more than 2 photons or etc. So these are just given by these coefficients out front. And I think so. Yeah, these are just these coefficients out front. And you can actually rewrite them using previous notation in terms of the channel transmissivity and the NB. So this is the physical number of background photons. Eta is the physical, attenuation factor. And so you can write these in terms of these things. So this is the successful transmission. This is you just getting random noisy photons. This is the receive nothing. Receive nothing is sort of okay because, oh, I didn't get anything. The bad parts are the random photons are receiving more than 2 photons. You can maybe even count these out, the receiving more than 2 photons, if you have photon number resolving capabilities. So if you can say, oh, I'm looking for a single photon, but I received 2, and then discard that event. And so then all you have to look for is, then all you have to worry about is random photon or, and your successful, the photon you want to transmit. Okay. And to a good approximation, a lot of times, especially if you have low background noise like optical frequencies, it's these two that are combating. So another question. It seems like Anthony is in superposition due to he can't. What is okay? Let's ignore that. Okay. So here's an exercise, which I think is intuitive. And so assume that this background number of photons is very low. And so in many cases of interest, at least of physical interest, this is what you want. This is the regime you want to be in. And expand all of these probabilities to first order in NB and show that the NB greater than 2 photons is equal to this result, so linear in NB. And can you intuitively explain? You can just use Taylor expansions. These are quite simple to do. I won't go through these. However, I will explain the result. And this is actually quite easy to it's quite easy to do. So what is the intuitive explanation here? Yeah, greater than 2 photons. Yeah, it's actually the first order thing is that you transmit your photon with probability eta, okay, and a noisy photon comes through with probability 1 minus eta, and then the number of photons, and that has to be related to the number of photons, okay. And there's two possibilities for this to happen because these are bosons, and you can't tell they're indistinguishable particles. You can't tell the difference at the level of this beam splitter interaction. So after they overlap, so there's two possible ways for this to occur. So you transmit your photon through by eta, but at the same time, with probability 1 minus eta, a noisy photon gets through. And so that's where this result is coming from. And using this intuition, you can actually guess a lot of these kind of probabilities. So it's useful to just line it up with intuition. Oh, okay. So I think that's the end. Which is I think good time to stop. Just a quick recap. I'll say a few words, and Quntao can say a few words. So just quick recap. So discussed how photons are good for just about anything: sensing, computing, communication, even good for quantum error correction. We reviewed some general descriptions of evolution and quantum channels. So there's Kraus operators, purifications, unitary extensions, things of this sort, some more abstract. Analyzed these bosonic channels, loss, amplifier, additive, Gaussian noise, and these are all useful in various contexts, optical transmission and microwaves, etc. And particularly their influence at the single photon level. Okay, so that's especially thermal loss and things like that becomes very important when you're trying to communicate single photons. Also did a little bit of photon encodings and single qubit operations, like these passive operations on dual rail qubits. So there's your quick recap.
Great. Thanks, Emily, for summarizing. I hope you find the course helpful for your either research or study. Yeah, that's the end of the course.